Hello and welcome. In this video, I'm going to go over some tips on how to start solving challenge problem 1. I'm just going to focus on how to set up parts A and B because all the other parts follow from that. But if you can't start the problem and solve for the two unknowns, then you can't proceed with any other considerations. And those two unknowns are going to be the angle of the electric field and the tension. But of course, we need to take a look at the picture. Okay. Now, I won't be plugging any numbers here, but I will be focusing on the free body diagram and a technique for solving for one of those two unknowns, which is harder to solve for, which is the angle. Okay, so let's take a look at our system here. This is not quite equilibrium, but it's a snapshot in time that looks like equilibrium. Because this is a centripetal acceleration problem, so we have a very well-defined acceleration and an acceleration that's dependent on other variables in the system, and that's why you can solve it essentially like an equilibrium problem. So what's going on? What are the forces we need to consider? Well, we've got gravity, because there is gravity in this problem. Okay, it may be normally much smaller than electric forces, but it can matter in a problem like this. Okay, because of course this is an electric problem, an electric field problem. And then we've got a force acting on our particle from the electric field shown here. Okay, well, let's take a look at the sign of charge. Okay, it's a positive charge particle, which means the force from the electric field is going to be pointing parallel to the electric field, not anti-parallel as it would for a negative charge. So that's supposed to be the same angle as E, and this is the force from E, okay? And so that means we know that the angle here is also phi, because the angle of the force, right? So we'll label that. Are there any other forces? Yes, there's the tension force. Okay, so we'll draw that in there. That's one of the things we're asked to solve for in part B. Now, if I'm being honest, you actually don't want to, under normal circumstances, and with the method I'm going to suggest, solve for A first. You actually want to solve for B first. So think of them as coming together, and the order could have been changed. All right, so we've got all our forces in here. One thing we want to quickly consider is what do we want for our coordinate axes? Because in a problem like this, a problem that involves centripetal motion, so that means, we're going to have some radius of circular motion. Do we want to set up a coordinate system that is, say, relative to the string, kind of like a pendulum problem, with a tangential component, a t component, and a radial component? Well, no. In this problem, especially because the electric field is measured relative to the x-axis, and we got gravity pointing straight down, we actually want to set up a traditional coordinate system with vertical and horizontal. So let's draw that in. All right. And that's just a big consideration in any force problem. That's why I spent a minute discussing it. Okay, we're ready to draw or write out the sum of forces themselves. Yep, I should be able to put them right over here. So we have F net X and F net Y. Okay, I'll expand it a bit as we fill things in. So in the X direction, we're going to have a negative component of the electric field. So I'll have negative and then QE. And the X, if we look at this, considering this is the hypotenuse, X is, well, horizontal, which is adjacent relative to the angle, so it's going to be cosine. So it'll be cosine of phi, one of the things we're trying to solve for. Then we've got tension, all right? Tension, I didn't draw the angle in. I'll do that now. It's going to be the same angle as the known deflection angle of our conical motion. Because this is often called a conical pendulum or conical motion. Because if you think about the swing and continue it in 3 dimensions, it makes a cone. So, and then the top angle of that cone relative to the center line is theta. Okay, and we know that number. So we'll go ahead and put in the tension, which is also negative. So it'll be Ft, and then for the horizontal component, this one is sine. So it's sine of theta. All right. Now, the other thing in the x direction, which I'll need a little bit more space for, is it's not going to be equal to 0. The forces in the x direction definitely don't sum to 0, okay? They have to sum to the centripetal acceleration times mass. That's going to look like mv squared over r. okay? Which on first pass may seem like a bunch of other unknowns, but we actually do know these quantities because we can relate R to L and theta. See, L and theta. And then V we can express in terms of the given omega. Okay, so we'll clean that up on the next step because I want to, again, show you how to solve for phi. But let's finish up with the sum of forces in the y direction. Oh, what do we got? Well, we got F T cosine theta, and because it's positive, and then minus just plain old mg, right? Putting straight in the negative y direction. We also have a component of the almost said gravitational force, but of the electric field force. So that would be negative q e, and that one is sine phi. Very good. Okay. So there you go. That's the big setup of identifying all the forces, making sure we have the signs right. And that comes from following the picture and choosing the coordinate system. Okay, so let's just show the next step. All right, I'm gonna write it down here so we're gonna have nice long lines. We'll write F net X. Nothing else to change here because we know Q, we know E, we know its magnitude. So they're both known quantities. All right, here's our other unknown, tension, but we know theta. Okay, so as promised, I'm going to rewrite the right-hand side. V, well, V is equal to omega times R, okay? So that means we can replace this with omega times R, but I'm not going to write R because I'm going to show you quickly over here what R is equal to. So let's draw a line here that represents R, all right? Okay, so this is going to be the radius of rotation. That's the radius of the base of that conical motion. All right, well, how do we then solve for it? Well, let's think about this triangle. We know that sine of theta is equal to opposite over adjacent, or R over L. That means that R is equal to L sine theta, and we know L. In fact, it's the one known quantity that we haven't used yet. Okay, so then we'll go ahead and write that in. That's going to be L sine theta, that whole quantity squared. And then down below, we have another R just by itself, which will then also become L sine theta. Okay? So you're going to see you're going to have an L sine theta squared and an L sine theta not squared. One of those are going to cancel. So we'll still have an omega squared, but it'll just be omega squared times L sine theta. Okay, and then we don't need to do too much reproduction on the next step. We just write F net, or too much expansion, I should say. It's just straight up reproduction. But I will need both equations next to each other. All right, so how do you solve this, right? Because we have two unknowns, phi, which shows up in both equations, once on a cosine and once on a sine, and tension, okay? Which shows up, of course, in both equations as well. How do you solve for one? Where do you start? Well, if you try to just go ahead and solve for part A and just directly solve for theta, although possible, it is very tricky and very easy to make mistakes. It's better instead to eliminate theta and solve for tension first. How do you do that? Well, I'm going to just describe this step because I want you to work it out. This is the solution. You solve the top equation, F net x, for cosine of phi. Okay, just isolate the whole cosine by itself. That's going to leave a big fraction on the other side. Okay, some big term with and with some terms in the numerator, and then as you can see, an e, or rather a QE in the denominator. And I'd factor out a negative so you don't have like a leading negative. But regardless, then once you have that, you're gonna solve for cosine of phi from F net x. Very similarly, you will solve for sine of phi from the other net force equation, the y component one. Okay, why would you do that? Well, think about it. Then you're just going to have the cosine phi and sine phi completely isolated. They'll both be equal to some big expression, but they'll be by themselves. Well, then you can eliminate phi altogether by then adding the square of both of them. Okay, so take sine theta phi, right? But substitute it in with all the other variables, including tension, okay, plus cosine squared phi equals 1. Because this is a true identity, right? This is a trigonometric identity, and we're using it as a way to eliminate phi. Because we know sine theta in terms of other variables than theta. We know cosine theta in terms of other variables than theta. We just square both those sets of variables, and we have this big expression, but with no phi in it, only a single unknown, tension. And then you can just do normal algebra, cancel out a bunch of things, combine like terms, and solve for tension. Okay? So that's the approach to solving this problem. Once you have tension, then you'll plug tension back in to either equation. Probably easier to plug it into the F naught y equation, and then very simply solve for phi with a single inverse trig function. Okay? And just make sure phi's in degrees. So that's the approach to get this problem started. Everything else will follow, because at that point, you know all the numbers of the system. You know both the unknowns, phi and theta. Okay? All right, well, I hope this was a helpful video. Thank you so much for watching.